All right, and welcome to the 6.2 intro video. Apologies for the location. It's been a long semester. But anyways, let's get right into it. This section is about learning how to take power series that say functions that we've represented as power series coming from the previous section in 6.1, and how to manipulate them to create an even larger repertoire of functions that we can represent in this manner. And we're actually going to push that. The whole of chapter 6 continues developing this idea. So even though right now we're frankly limited, I think, to exclusively geometric series, theories that we can represent as a geometric, courtesy of the geometric series test, thanks to the magic of Taylor series, which you'll learn about shortly, we're going to push that quite a bit further. And all of the techniques that we develop here, which we'll use in the context of geometric series and their derivatives, their integrals, sums, differences, products, whatever, that extends verbatim even when we've learned Taylor series and other ways of representing functions. So I think there's no better way to get into this than just by going to the definition or going to the iPad and working through some examples. This is going to be the like with many of my videos, it's going to be a touch long-winded, and it will be the intro video and the worked example video all rolled into one. So my expectation is that you are reading the book alongside this. You can pause the video and work out an example when we call it. All right, so to do this, we're going to start with the standard building block for this section, which is that we can express the function 1 over 1 minus x as a simple geometric series, x to the n. And of course, just to be clear, although hopefully it's clear where this is coming from your 6.1 reading, what's going on is that this is a special case, if you will, of a geometric series that look like this, where we have a is equal to 1 and x is equal to r. And we know that this geometric series, as long as r is less than 1 in absolute value, converges to a over 1 minus r. So simply making the substitution that a equals 1, making the substitution that x equals r, and with the stipulation in place that the absolute value of x is strictly smaller than 1, we get that this geometric series represents this function of x. And this represents a huge step forward for us in terms of the idea of representing a function as a series. Basically what's going on, and as I think we said at various times, I'm pretty sure that JJ's admittedly long intro to Taylor series says this. The idea is that ultimately we want to study expressions of this form. We want to know where they identify, where they sort of agree with other functions that we can write down. And again, right now we're pretty limited in what we can do. We're going to change that. And an expression of this form makes sense for all the x's, all the x values, such that when you substitute in, so here's what I want to say. Let me try this again. This is a function whose domain is the set of all the x values, all the real numbers, that when I plug in that real number, I get a convergent series. So we know that no matter what real number r I plug in, we would get a geometric series with r as the common ratio. And we know that converges when r is less than 1. So in other words, we'll think of this as a function defined on all the x's which are less than 1 in absolute value. So in other words, this definition is -1 to 1, open parentheses, because we're not including the endpoints. And then we're going to be interested, when can we write down another function that represents the same function on that interval? And it's important to note that even though this function, so this function has a problem at x equals 1, that's no good. It does not have a problem at x equals -1, however, but our series does. So they're not always going to agree. In fact, that's pretty common. But where they agree, in other words, on the interval -1 to 1, these two expressions will give the same value for any real number. It just happens to be that this one can be defined more broadly than this one can. They both have problems at 1, but this one also has a problem at -1. -1 is no good. Okay, so that was just a brief aside on where that expression was coming from. But now what I want to talk about is how can we use this to write down some more general formulas. And there are a couple things that we can do. So one is we can, well, technically the first one that the book talks about is adding and subtracting, but they do everything with very general symbols. I want to just develop another practical example for the moment. So what about say 1 over 1 plus x. So we can write this as 1 over 1 minus x. And therefore, by the same expression, or the same realization we used a minute ago, we can represent that. Notice here, I'm thinking of this. This is the usual expression where this is my first term, a, so implicitly a 1 here. And this now is my common ratio, which is why I have a minus x instead of an x. And I can rewrite this. Let me give myself a little more space. I can rewrite this, thanks to how exponents work, as negative 1 to the n, x to the n. And so in particular, both of these converge for x strictly less than 1 and absolute value. So they both converge on the interval negative 1 to 1, open parens on both sides. And so in particular, I can put them together. So I can write down an expression for this sum. On the one hand, what is that sum? Well, let's see. So it would be 1 plus x plus 1 minus x all over 1 plus x, 1 minus x. So here all I've done, cross multiplying and putting everything over a common denominator. And this simplifies, of course. So this is simply what? 2 over 1 minus x squared. Okay, so this is actually a really cool example, because if we're good, and we'll see in a second that we can do this, we actually could have figured this out directly. But now what I'm claiming is that we know how this is represented. We know how this is represented. We can add them together on the interval where they both converge. So this is the sum from n equals 0 to 1 of x to the n, plus the sum from n equals 0 to infinity, infinity, of negative 1 to the n, x to the n. And if we think about it for a minute, what's going to happen? Well, on any time n is even, this negative 1 to the n is going to go away, and I'm going to get the same term summed twice. And anytime n is odd, this becomes a negative 1. The terms are going to kill each other. So if you think about what the first couple terms of this series look like, it's 2 plus 2x squared plus 2x to the 4th plus 2x to the 6th. So again, just to be clear what's going on here, the odd terms are dying because they are being subtracted. They're being added and subtracted, so they're canceling each other out. And the even terms are being doubled up because negative 1 to an even number is just 1. So you're counting it twice. We can write this, we're very good at infinite series, as x to the 2n. 2 times the summation from n equals 0 to infinity of x to the 2n, which if you like is 2 summation from n equals 0 to infinity of x squared to the n. But hey, hold on a minute. I am actually this excited. I love this section. I love messing around with the Taylor series. And for what it's worth, if you go on to take other math classes, Math 35, Math 36, I made my Math 20 students do this, a multivariable. Yeah, we do this a ton in the 35 class, which is the advanced calc class. This is how you determine the sum, the expectation and the variance of like a geometric random variable. It has to do with manipulating these sums. They in Math 36, it shows up a lot. It's actually, again, it's like a game. I think it's a lot of fun. Somewhat weird. That's why I'm a mathematician, but anyways. But look at what happens here. This is a geometric series. This is a geometric series with a being 2 and r being x squared. And we know what a geometric series converges to, assuming that the radius, of course, is less than 1. We're going to come back to that in a moment. What would this series converge to? Well, it's a over 1 minus r. And what do you know? They work out to be the same thing. In fact, that's not at all a coincidence. It's going to happen literally every time. So anytime, basically, that you can manipulate these series in some way, or the functions that represent them, you're going to get the same thing on both sides of the equation. So here we took a function that we could have written down directly, as we now see, but instead we wrote it down as some combination of functions for whom we knew the Taylor series. And we went ahead and manipulated that, and in fact, everything worked out. I'm going to do a slightly harder example of this that I think is even more impressive, but I'm actually going to pause the video first to work it out beforehand because it's not easy. And this has to do with what happens if we multiply them together. So give me a second. Okay, Okay. Actually, I'm too lazy to work it all out, so let's just do it. I paused the video and was like, I don't want to do this twice, so let's just do it. I actually do like it. So despite not wanting to do it twice, this is actually really cool. So let's take the following function. 1 over 1 minus x squared. Now, on the one hand, this fits the bill of a geometric series where, again, a is 1 and r is x squared. Because remember, the general formula for a geometric series is a over 1 minus r. So notice that this example that I just wrote down fits into that. And so in particular, this function can be written as long as we have r less than 1. So I didn't make a big deal of that in the last case. I'll make a bigger deal of it here. This can be written as, so a1 times x to the n, or sorry, r to the n. But remember, r is x squared. Remember, the formula is a over 1 minus r, so the minus is fine. The r here is just x squared. This is just the summation from n equals 0 to infinity of x to the 2n. And it will converge wherever x squared in absolute value is less than 1. Just a reminder real quick, because it's going to come up a lot, including on the Friday assessments, that the absolute value of x squared is the same as the absolute value of x squared. And I can apply square roots. Square roots do not flip the inequality. So this will be true exactly when this is true. The way to understand that is square roots are, so the square root function is an increasing function. So if I have that a is less than b and I take square roots of both sides, it will still be true that square root of a is less than square root of b. That's all we're using here. It has to do with the fact that it's just a monotonically increasing function. All right. So what else could how else could I have done this though? So on the other hand, this expression is this product. And we know how those things are represented. So we have to be careful. The way that you're probably going to want to multiply power series is not the way they multiply. There's a name for what you want to do, but I'm not even going to bring it up because I don't want you to get in a bad habit. So how is this represented as a power series? How is this represented as a power series? And what on earth do we do to put them together? So this first term is, of course, just n equals 0 to infinity, x to the n. The second term is n equals 0 to infinity minus x to the n. Remember, we have to secretly write this as 1 minus a minus x, because you always need that denominator to be 1 minus r. All right, so how on earth do you multiply power series? Well, the answer is the same way you multiply polynomials. You just have to FOIL everything out. So if we think of this, and we'll just write down a couple terms. It's difficult in general, actually, to recognize what's going on here. We'll just write down a couple terms. So let's write out like the first 4 terms of each of these, and then we'll put some dot, dot, dot. So this is 1 plus x squared plus x cubed, dot, dot, dot. So that's just expanding out this term. The ellipses, of course, are exactly why the sigma notation was developed, so we never had to write them. I think it's easier, however, when you're starting this to do it this way. And what are the first terms here? So remember, the sign is flipping. So this is 1 minus x plus x squared minus x cubed, dot, dot, dot. Okay, so how are we going to multiply this together? Well, again, we just FOIL. So what do we get? So it's going to be a little tedious. I'm going to take this term and I'm going to multiply it by everything over here. Then I'm going to take this term and multiply it by everything over here. Then I'm going to take this term and multiply it by everything over here. It'll go quickly. So we get 1 minus x plus x squared minus x cubed plus x minus x squared plus x cubed minus x to the 4th. Now we're moving on to the x squared terms. I'll group the terms so you understand these are all the terms that correspond to 1. These are all the terms that correspond to x. So we keep going. Plus, so these are the x squared terms. So x squared minus x cubed plus x to the 4th minus x to the 5th. These are all the x squared terms. So we'll throw some red. Okay, and then finally, plus, and now we're going to do the x cubed term. So x cubed minus x to the 4th plus x to the 5th. It's a horrible 5. Minus x to the 6th. All right. And of course, in reality, these terms would keep going. But all I want to understand is, what do the basic terms here look like? So you will notice we have only one constant term. It's right here. So we get a 1. Constant term is a 1. What's our x situation looking like? Well, we had a minus x and a plus x, and nothing else contains an x, because as you'll notice, all of these terms are at least a square, all of these terms are at least a cube. And in fact, that's generally going to be true. If you think about it, just like with polynomials, the only way to get a product that has a certain degree, the only way to get a product, a cubic, for instance, is either a constant and a cubic, a linear and a quadratic, or they switched, and a quadratic and a linear, and a cubic and a constant. That's it. If you have only terms of degree 5 or higher, there's just no way multiplying it with any polynomial to get something that's cubic. So this is generally going to happen. So the x terms dropped out entirely. Now what's going on with the x squared? Well, we pick up an x squared, we lose the x squared, and then we pick it up again. And there's nothing here that can be an x squared. So this is plus x squared. How about x cubes? So we lose an x cube, but it cancels. We lose an x cube, and it cancels. It's gone. And you'll notice now we've exhausted all of these options. X to the fourth. So we lose an x fourth, we gain an x fourth, we lose an x to the fourth. Does that sound right? Nope. Hold on. So where minus is, hold on. So we should get plus x to the fourth, but I'm getting minus x to the fourth. So why would we work out examples ahead of time? That was never a question. So let's figure out where on earth I went wrong. So where did this x to the fourth come from? It came from x and negative x cubed, so it is a negative. That's correct. Hold on, I see. Ha 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 ha. Okay, this is the problem with ellipses. So, right, so I'm getting the wrong answer. I said, so this again, this is why it's difficult to multiply in real time, or why it's difficult to multiply a power series. We said that this should be x to the 2n. That means every sign should be positive. Notice that I have an x to the fourth here, and an x to the fourth here. Those are going to cancel. But I pick up a minus x to the fourth here. So it would look like that I should get a minus x to the fourth, but I know that can't be right because I know the theorem in math tells me that these two series have to be the same. So the question is, what on earth happened? Well, two things happened. We missed two x to the fourth terms. We missed an x to the fourth term that would have come from this one times this x to the fourth. That's where I started writing my ellipses. So if you thought about it, if you think about it, the next term here would be x to the fourth, and indeed it would be plus. So here's a plus x to the fourth that we missed. The other one that we missed would be this product. So in fact, there would be two more positive x to the fourths. I'm just not seeing them because I stopped writing too soon. So in fact, this is plus x to the fourth. Again, if you filled out, if I promise you, if you wrote the next term, x to the fourth, and x to the fourth, and carried this out one more step, you would see that this is plus x to the fourth. But again, this is exactly why it's very difficult to multiply power series, because they just keep going. And indeed, there's no point in going on. But hopefully, again, explaining to you where the missing x fourth terms come from, hopefully you can appreciate this series is starting the same way as this series, and indeed they would be the same. And you can actually write down an expression for what's going on. You could actually figure out that the coefficient on a given term would be 0 if it were negative, if it were an odd power, and 1 if it were an even. Basically, due to some cancellation, you'd have to work out the pattern, basically. And the way you prove that, in fact, sort of rigorously, is something called mathematical induction, Math 23B, Introduction to Proofs. Fantastic class. I believe CS 29A also does it. Between you and me, less fantastic class, but not bad. So you would still pick up this reasoning in CS 29, but honestly, just take Math 23B because it's a phenomenal class. But again, this goes to show you this is difficult to do. It is difficult to multiply power series. It's very easy to add them. It's very easy to subtract them. It's very easy to multiply a power series by a polynomial. So a special case of this, which is much easier to see, is that, for instance, if I take my function that I know, like 1 over 1 minus x, and I just want to put an x squared or something up top here. Well, so actually, let's see what this should be. So on the one hand, thinking of this as a series, and thinking of this as a for the moment, and this as r for the moment, this should be the summation from n equals 0 to infinity of, well, a r to the n. And that's the summation from n equals 0 to infinity of x squared times x to the n. And you'll notice that you can just write that as x to the 2 plus n. On the other hand, we could have separately thought of this as taking x, the function, 1 over 1 minus x, and simply multiplying it by x squared. Now, we can turn this into a power series very easily, and the x squared just sticks around out front. Again, this is a very special case of a power series, but it's a very silly power series because, in fact, it's just a polynomial. Those are special. I don't actually know if your book would consider that a special case. I guess it depends on what their definition of power series is. But in some sense, in the sense that power series are a way of making sense of infinite degree polynomials, regular polynomials are sort of just power series that end. And actually, probably, I guess technically it would be, you would just take all the coefficients to be 0. I know none of you are interested in this. This is what we do. So the point here is that I can just take this and bring this inside. And so this is going to give me the same answer that I got right here. And again, not a coincidence, that will always happen. Okay, I've gone on for too long, so let's talk about the most important thing that we can do. Adding and subtracting is nice, multiplying by polynomials is cute, plugging in a larger value, that's a nice trick. So again, you'll notice we've done that a number of times, and it's going to be true a lot more generality. But for instance, like here with the 1 over 1 minus x squared, wherever it is, here. I just thought of x squared as the radius, the ratio instead, and I just plugged it in for r. But one of the most important things that we can do, and a big theorem in this section, is that if you have a power series, then on the interior, at least, of its radius of convergence. So we have a power series. On the interior of its radius of convergence, we can differentiate or integrate termwise. And in fact, you can, the text does a good job, I think, of acknowledging the subtlety about this, but in fact, the endpoints generally work as well, but it follows from something called Abel's theorem that is outside the scope of this class and the book, but you can go read about it on Wikipedia. I never leave myself in front of when I write. So this is called Abel's theorem if you wanted to look it up on, say, Wikipedia, so you can see what it says. Let's see a concrete example of this, a really cool example of this. Let's look at the alternating harmonic series for a moment. So this is, of course, the series n equals 1 to infinity, negative 1 to the n, over n plus, I guess the way I've done it, I guess it's negative 1 to the n plus 1 over n. Okay, so this is a series which we know converges conditionally. Let me just remind you of that. So this converges conditionally. So we know that it does not converge absolutely, because if you throw absolute values around it, you get the harmonic series. Harmonic series is the example to keep in your back pocket of a series that diverges, even though the divergence test couldn't tell you that. But this converges by the alternating series test. So this conditionally converges. It is this incredibly cool theorem. Your instructor may or may not have told you about. I tried telling my class about it, but it's a little subtle to take in. It's called the Riemann rearrangement theorem. It says that if you have a conditionally, I'm going to write that down because it's actually really cool. If you feel like getting into some, does Riemann have two? If you feel like getting into some Wikipedia rabbit holes, search Riemann rearrangement. It says that you can rearrange a conditionally convergent series to converge to absolutely any number that you want, or diverge in anything. This is not possible, interestingly enough, for absolutely convergent series. If you take the terms of an absolutely convergent series and you mix them up and you rewrite them in some different order, they'll actually converge to the same thing. So that's, I think, everyone's normal expectation. So this Riemann rearrangement theorem is actually quite a wild theorem. So in particular, if you want to talk about what a series like this converges to, we have to say what order we're using, but I'm going to use this order. So what does the standard alternating harmonic series converge to? And notice that it's not geometric, so none of the theorems that we have at present can furnish an exact answer. It is alternating, so you could use the alternating series test as a remainder form of that to get a good approximation, but we don't know what it converges to exactly. But now we're going to see. So how are we going to see? I actually have to remember the setup for this. So I'm going to start with the formula. Okay, hold on. I'm going to cheat because I got to remind myself. This is actually an example of the book because it's a great example. It should be an example of the book, but you have to get the right starting point, which is why this is still hard. Coming up with the exact value of a series is difficult because if you're going to do it this way, like I'm about to show you, you have to sort of think through very carefully where you want to end up and where you had to start to get there. Okay, so welcome back. So we're going to start with this series, 1 over 1 plus x that we saw a second ago. And we know that this is a geometric series. Again, I will, and it's good practice at first, to always write it in this way. So you have the minus. That means this whole term here is a word. So this is equal to the summation from n equals 0 to infinity of minus 1 to the n, x to the n. All right, cool. And this works on x from negative 1 to 1 exclusive. So this holds, just as a reminder, for all x in this interval. Okay, cool. So now we hit this theorem in the book that says, well, I can integrate both sides and the radius of convergence is guaranteed to stay at least this large, and I'll have to recheck endpoints. So let's try that in this case, actually. So I want to integrate both of these expressions. This left-hand side is very easy. I get ln of 1 plus x. Now, technically, that should have absolute values, except I don't actually need absolute values because our interval, no matter what x you take in this interval, if you add 1 to it, it's non-negative. But that's okay. I'll leave the absolute values for the moment because it's good practice. Now, on the other hand, this is a non-trivial thing, even though it's going to look very natural to you. Part of the beauty of power series is that I can pull, because they converge absolutely, so that's an important point. Power series converge absolutely on the interior of their interval of convergence by the ratio test, which proves absolute convergence. I know I just said a lot of words there. It's worthwhile to listen to that video a couple times to understand it. But the ratio test tests for absolute convergence. And we use the ratio test to determine the interior of the radius of convergence. Doesn't work at the endpoints, so these they don't have to converge absolutely at the endpoints, but they will converge. The power series will converge absolutely on the interior, so away from the endpoints of the radius of convergence, or the interval of convergence, I should say. And what that means is I can pull this summation out. So this says that what I get is the summation from n equals 0 to infinity of the integral of negative 1 to the n, x to the n, dx. That's what that says. And in fact, if I wanted to, and why not, I could even pull the negative 1 to the n out, because who cares? That's a constant, so that can always be pulled out. So we get this. This is a non-trivial thing. Also, it's interesting. There are calc books out there, although I don't think this is the right way to go about it. If you get really good at understanding how to represent functions as series, and every function we've ever written down can be written as a series, then if you're comfortable just converting the function you're interested in to a series, you only ever have to integrate monomials. So you could actually teach calculus and teach integration. Again, I don't think it's a good way, but I've seen at least one book that tries this without ever writing down integration by parts, partial fractions, U substitution. You don't need any of them. Trig subs, you don't need any of them. So if you get really good at manipulating series and you can integrate term-wise, you'll only ever integrate these terms, or x minus a at the end, maybe. So maybe they need a very simple case of U substitution. All right, so what do we get? So this becomes summation n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1 plus c. Okay, don't forget your plus c. It is an integration class after all. So we need to figure out what the plus c is. That's tricky, and students do struggle with this, but I want to point out I have a real easy choice of x that I can plug into both sides where everything gets made very easy. What value of x can I plug in that will kill basically everything here? Not quite everything, but almost everything here. Can plug in x equals 0. So let's plug in x equals 0 to both sides of the equation. So plugging in, I'll write it down, plugging in x equals 0 yields ln of 1 plus 0 which is ln of 1, which is 0, is equal to, now what's going to happen in my series? So every term that has a positive power, 0 to anything positive, is just 0, and it's absolutely going to vanish. The one exception to that is when n is equal to 0. So 0 to the 0, as weirdly as it sounds, you have a bit of an issue here, because we say that 0 to the anything is 0, but anything to the 0 is 1. So you get an issue about how to actually handle 0 to the 0, but mathematically we define 0 to the 0 to be 1. So if you plug in n equals 0 through, I see, never mind, it was moot, because even if you plug in n equals 0, your power starts at +1. What do you know? So actually, everything I said is true. It just doesn't matter here. 0 to the 0 is mathematically generally defined to be 1, but it doesn't matter here. If you'll notice that even at n equals 0, I would get -1 to the 0. That's 1. 0 to the 1. So that's just 0. So this is C. So C is 0, because that's what the left-hand side equals. All right. So in other words, we have a series expansion. This is probably our first non-trivial series expansion that says that log of 1 plus x can be represented by this series. And you may notice that the alternating harmonic series comes from plugging in x equals 1. Now that's a little bit tricky, because our original series didn't converge at 1, right? This series, we have to omit 1, because it doesn't actually work. But interestingly enough, when you integrate, you can actually pick up those endpoints. So we should check. So we're going to check real quick. So does this series, by that I mean this series, converge at x equals 1? So does this converge at x equals 1? Again, when we took the derivative, it didn't. But now that we've integrated, well, I should say the original series, that's a better way to say it. The original series we started with did not. This series, because it's coming from a geometric series, requires r to be strictly less than 1. So in particular, we get this open endpoint, this open interval. But again, it turns out that by integrating, you can actually pick up the endpoints. So does this converge at x equals 1? Well, so at x equals 1, what series do we get? We get -1 to the n over n plus 1, which you could shift the index if you wanted to say n equals 1. You'd have to shift this up as well over n, and this does converge by AST. So in fact, even though our original series only converged on -1 to 1 open, this series, you should check, by the way, it doesn't work at -1 because, oh wait, no, it doesn't, -1, hold on. -1 to the n times -1 to the n plus 1. Yeah, it's just negative. Oh, okay, so yeah, it works both endpoints. Hold on. Shoot. Give me a second. Got it. Sorry, it doesn't work at -1. I was thinking that there was going to be some sort of alternating sign. There isn't. So just as a check, just as a note, because again, it shouldn't work at -1, partly because this function does not work at -1. So real quick, what would happen if you tried at x equals -1? So this is the series that I would get. So again, all I did was just like before, where I took my x and I replaced it by, well, 1. So I guess implicitly it was here. Now I've taken my x and I've replaced it by a -1, but this -1 still comes through. So I don't get to get rid of it. You'll notice that -1 to the n times -1 to the n plus 1, that's -1 to the 2n plus 1. 2n plus 1 is always odd. That means this power is always -1. So this is the same thing as the summation from n equals 0 to infinity of -1 over n plus 1. Again, you should check that. So if n is 2, for instance, -1 squared times -1 cubed, well, -1 squared is 1, and -1 cubed is -1. So that'll be -1. What if n were odd? -1 to the 1 and -1 to the 2. Again, -1 squared is 1, -1 is 1. Sorry, -1 to the 1 is -1. So it always will work out to be -1. This series diverges because it's just a constant multiple of the harmonic series. So our new series representation that we've written down is ln of 1 plus x can be expressed in a series. And again, we're going to see this series in the next chapter on the interval -1, 1 inclusive. And so in particular, you can ask, what happens if I plug in 1? If I plug in 1 here, I get the alternating harmonic series as we observed just a minute ago. But if these are equal, you might hope that I could plug in 1 here. Technically, and again, this is where Abel's theorem comes in, technically, the theorems in the book don't actually allow you to do that, but it is mathematically correct. So you need something, our book is only telling you what happens on the interior of the radius of convergence. We've picked up an endpoint in our process of integrating. You would hope that you could still plug in on both sides and it would be correct. That's not technically given to you. I know this is a very technical point, but it's not given to you. It's not guaranteed by the theorems of the book, but it is guaranteed by some theorems that simply don't make the book. And so in particular, plugging in at x equals 1, where we know the right-hand side converges, we know the left-hand side is fine, and so by Abel's theorem, they have to agree, we get that the alternating harmonic series, I'm going to go ahead and rewrite this in the usual manner, but I promise if you check, it's just a shift of index, doesn't actually do anything different. This is equal to what happens. So all I did was plug in 1 on the left-hand side, so it should be equal to what happens when I plug in 1 on the right-hand side. And this, I think, represents the first series that isn't telescoping and isn't geometric, that we can actually say what the value is. But as I've said, and as you've seen, I'm sure, and I think the book mentions as well, even a series as simple as 1 over n cubed, so p series with p equal to 3, that value is unknown. There's a monetary award if you can actually prove what it is. So again, it's very challenging, and not every series, at least to our, if there is a function floating around out there that we can write down a series for and get it to converge and find a value in this way, well, clearly we haven't found it. I don't actually know if we know that such a function cannot exist. Sometimes we do know that. Math is really an incredible field. I don't actually know in this case if we know that such a function can't exist or we simply haven't found it. But again, here, by starting with a function, and it's kind of convoluted, the logic, right? If you had started by wanting to know the alternating harmonic series, there'd be quite a bit of thought that had to go in here. You'd have had to figure out some series that you could write down, that you plugged in a value and got the thing you wanted. You would need to know that that series was obtainable from some other series that you could write down a function, a closed form for the function in some way. So again, in this case, the whole thing started with this geometric series, which we're comfortable with, whose integral becomes the log, and such that when I integrate the series aspect over here, I get something that when I plug in 1, I get what I want. But then I needed to know that they converged at 1, that they agreed at 1. Again, none of this is obvious. So that's what happened. So we wrote down where this function was represented by this series. We had this interval. We then took the integral of both sides. And again, the theorem says that that's okay, that works. We did get a value of c, which we needed to figure out what c was. So now we have an expression for log in this manner. And we went ahead and checked. And again, the theorem says that you can sometimes pick up endpoints when you do this. So we checked, and lo and behold, we did actually pick up that it worked at 1 by the AST, does not work at -1 still. So in this way, we've now expanded our interval of convergence. Previously, it did not have the endpoint, but now it does. And then we have to invoke Abel's theorem. It says that since everything worked on the interior of the radius of convergence, and they both make sense at that endpoint, they still work, they still agree at that endpoint. And we went ahead and plugged in. So a ton of work, but very cool. And again, the expectation of the geometric random variable, I know there's a bunch of phrases that you don't know yet, but hopefully you will, because 36A is an incredible class, is also done by trying to sort of reverse engineer a series in this way. It's a really, really cool little exercise, unless you're taking 36A, and then it's terrifying because you'll have forgotten all of this. Hopefully not by the time you do it. Anyways, all right, I think that's going to call it for this video. You can also differentiate. The differentiation is easier. So in particular, you could have started with the same series, 1 over 1 plus x, written as negative, the summation from n equals 0 to infinity of negative 1 to the n, x to the n. And if I differentiate it, so what's the derivative of 1 over 1 plus x? It would be negative 1 over 1 plus x quantity squared. And then you would take the corresponding derivative over here, and you would get a corresponding series representation of that function. Again, everything works nicely as long as you're on the radius of convergence. All right, so again, we have a great chapter ahead of us, and I hope you enjoyed the reading because this is a lot of fun, and this is a really powerful technique if you internalize it and get used to it. All right.